Let's discuss the Bradford assay, which is used to determine protein concentrations. It's a colorimetric assay in that we will be looking at differences in absorbance. So, in the experiment, we had made different solutions with different concentrations of bovine serum albumin. And so, assuming a 1.00 milligram per milliliter, because that's what it's made up to be, solution, we then knew that we needed to have this amount of BSA added to this amount of water to make a total volume of 500 microliters. And then we took 10 microliters of each of those samples and we added them in triplicate to wells in a 96 well plate, and we put this in a plate reader, and we then read absorbances. We also had 3 unknowns. So the data that came out is what we see here is the first set of data did not have any BSA added, so that's our blank, that's water, and that shows us basically for that particular 96 well plate, they have different absorbance characteristics, and so for something without any BSA, this is how much it would absorb, and so that needed to be subtracted from the raw data for each of the points. So what we see is that in the first row, the first line of each row, we see the absorbance data, which is raw, uncorrected, without subtraction of water. We then saw for the second row, first of all, if you add these up, so this is what we're doing here, we add up the water, we divide by 3, that gives us our average water. And indeed, if you take the raw data that we saw in line 1 of a row, we subtract that average for the water, and we indeed get the calculated absorbance, meaning what's attributable to the BSA in that solution. We see that the third line in each row is actually the average of the second lines for each column. So here's like 0.3, 1.51, 0.69, and you add those up, divide by 3, you're going to end up with 0.81. We can enter that data into an Excel spreadsheet. Here's the concentrations in milligrams per milliliter of our standard solutions. So that's what we got from here when we put things together. Then we have the average from the program. These are absorbance numbers here. We see them again, line 3 in row 1, line 3 in row 2, line 3 in row 3. Those numbers are here, entered into the second line. Now, we're going to be needing to calculate the standard deviation. We're going to use standard deviation to create error bars for each of these data points. And so then we take the second line from each row and we put them here. And I'll show you in a minute how you use Excel to calculate the standard deviation. All right, so here is going to be an example. Now we're in Excel, and here's the numbers that we had. And to get the standard deviation, I will, just as an example, so I copied these numbers. To calculate standard deviation, you put your numbers in the Excel spreadsheet. You then click on a blank box below the numbers you want to include in the calculation, and you drag it up. You then go up to the FX, the function key. You'll see by clicking on it, you'll get a selection of functions that one could use for calculations in the Excel spreadsheet. So you click on standard deviation, you click on OK. you'll then get a pop-up box that will actually tell you what boxes are going to be included in that calculation. And you hit OK, and then you see it calculates a standard deviation for you. So if you notice, this is the same as here. That's how I generated this number. I made the table, then I clicked on an empty box, dragged it up, and told it to calculate. So I now want to use this data and show you how to make the graph. So for making the graph, so this is the final product, and you see these data points. Those are actually derived from the average absorbances. So I select the known concentrations of BSA. That's going to be my x-axis. And here's the absorbances, which is going to be my y-axis. I then go up to Insert, and I look over, and I'll see charts. And because I've been using it, my scatter plot chart is one of them. If it's not, you'll need to go into chart more into this until you get to scatter point graphing, scatter charts. There are different ways to do. You can see things happening already down here, but I just want the data points generated. So then I get my chart and my rough chart, and so you can already see, compared to this chart, I don't yet have my titles, I don't have error bars, I don't have my formula. So how am I going to get that? Look at the plus sign up here on the upper right. So you get over the chart, you hover over it, and then you click on it, and you'll then see all these different chart elements. So click off x-axis, error bars, trend line. You can leave off the data labels and the legend. So that generates this chart, and now all of a sudden you see places. I will be able to just click on these and type in what I want, for the chart titles and stuff. And then you see your data points, and you see this trend line. And then you'll see, we'll first work on the error bars. You see that by default, there are default values. They're all the same. I don't want horizontal error bars in this case, so I click on it, go to your keyboard, hit delete, and then those horizontal error bars are removed, and then you have the just the vertical error bars. Now there's at the moment all the same for each point. Now you've calculated using the absorbance data from the second line of each data row. You've calculated a standard deviation. So what you do is you go to the error bars, you go to this arrow caret, click on it, and you'll see different options. Go to more options, and then you'll see there are different things that could be here. You want to make sure that it's these column error bars. Make sure it's so you're going to have caps on it. That's the little things, and that you want it both. You see what happens if you go minus or plus, but we want both. Okay, so what we then do is go down to custom here, and then we set something called specify value. So we want to specify the values for each of those, which are going to be standard deviations. So we click on specify value. We get this pop-up, and then there's some default value. It's 1, right? So we want that removed. So activate it, delete it. Activate it, delete it. And then move your cursor, say, it doesn't matter which order you do this, but you go to the positive error value. You're then going to go up to the standard deviations, and you're going to drag your cursor across until you activate each of the standard deviations. And then you'll get this it put together sheet and a range of the standard deviations for each of these. And then you go to that's for the positive value, and you're going to do the exact same value. Again, you're going to activate that box, go up to standard standard deviation, drag it across the row, and it should be the same. And then you'll hit OK. And now you see that you now have error bars that are specific to each of the data points. And that's how you create and put in your error bars. So go again to the plus. Now you want that formula. Go to trend line, go to the arrow, caret, whatever you want to call it. Click on that. You'll now see different ways, that one can put in, do things to the trend line, but we actually want more options. Again, we have the bar graph activated, and we go down to the bottom, and we see that there's a display equation on chart and display the R value. And that then we see a formula. You can click on that and move it. Now I find that a little small, so I activate it. I myself go like to home, font. I prefer Arial myself. And I'll make it some size here. And I can read it. Then I can also type in, what I want for the X and Y axes. So again, eventually, once you put in the titles, then you generate this graph. And from this point, we're most interested in the equation that gets generated. So from the equation that we generated, we see the R value. Ideally, it's greater than 0.95. That would give us confidence in the data that the variation isn't so unreasonable that we doubt it. Okay. And we see our graph with our different values. So what we're going to do with this equation, which is we're going to be working with from this point forward, is we need to solve for x. So notice this is a y is equal to a constant times x plus some other constant value for the shift. So what we basically do is, if you have y minus this shift value divided by the constant in front of the x, and that solves it for x. We then can calculate the milligrams per milliliter. So for now we move to the unknowns. So we've generated our calibration curve. We have a formula for that, and now we can actually plug absorbance values into that equation to get calculations of concentration. So what we really want to do is what's the concentration of the proteins in our unknown. So we generated that curve. This curve represents our known concentrations versus the absorbance. So now we got to see, where do our knowns fit in this? Now we don't just go to the absorbance. Actually, we have to convert it to concentration data to compare concentrations, not absorbances. That's a oftentimes made mistake. So to get the concentrations, we just need to add an absorbance value into the y position for the y in this formula, and we will, because the y-axis is absorbance, we want to know what does that do for concentration on the x-axis. And so this is our formula for calculating x. We now see, if we were to take the average values, we can then calculate out the concentrations based on each of the average values. Here, I just happen to say unknown A, B, and C, which is actually columns 10, 11, and 12, respectively. And we can see a calculation that there's an increasing amount in each of these. Now, to get the standard deviation, which we're going to want to understand how accurate, how much can we trust that data, we need to do it for each of the absorbance values that were obtained from each of the rows. So again, that's the second line in each row for each of the data points. And so you plug it in. Just so happens to, like in this example, it's 0.05. Pay attention to decimal places and zeros, and you put it in. And so we see some calculations. Two of them are identical in this case, and one is higher. If we put it together, we actually add these, divide by 3, and there we get this concentration. It happens to agree with what we calculated using the average absorbance value. But depending on how you round, sometimes there could be a slight variation between using the average value and each of them. Okay, so you do this for each of the samples. See, here is 0.69, and here's 0.69 from column 11, sample B. 1.02, 0.12, and 0.08. And we did the same for the third unknown, which is in column 12. So here we have 0.1, and here's 0.1. See where this data comes from? Here goes to here. All right. So for the unknowns, we're looking at concentration data, not absorbance data. And that's the point I'm trying to make. So you can find this table in the form for reporting for the lab. And basically it summarizes all the data. So we see here are each of the columns, or rather each of the samplings. So here's the column for unknown A, and then here's each of the lines, you could say, the test number. So this is arbitrary a little bit. So anyway, but notice the concentrations here are those from the second line of each row from the appropriate column. So see where this data comes from? So this is just a organization of the data you've already worked with. Then we saw by using that formula that we were able to calculate each of these concentrations. So again, these are milligrams per milliliter. These are no longer absorbance. And then from our calculations, we saw that we had this average. You could use either. And that's what's going here. And then the standard deviation is what we also we could put them into an Excel spreadsheet, if you remember. And then we just, so here's this data here. See this, where this data was put into the column. So this data gets put this into the Excel spreadsheet, go click a box below it, pull it up, hit the function, get the standard deviation, which is actually in milligrams per milliliter. And that's what gets entered here. So for the lab report, this is it. Okay, so you see your average protein concentration for your unknown, and which is what we're trying to find out, what's the average protein concentration, and then how reliable is that data. We see in this particular example that 0.026, which is 0.003, is the most accurate, and the 0.016 is actually the least accurate. Based, this has the widest spread of data, and we can see that. So this ranges from 0.025 up to 0.057. Okay, so even though we're getting a 0.039 value, it's roughly correct. It makes sense looking at the absolute absorption data, but this has the greatest variation. If we look at this data, 0.51, 0.52, 0.55, I mean, already you can see that this is going to be close, and indeed we see that. So the standard deviation just means that if I had to place my trust in the accuracy of the data, I mean, I would consider this the most accurate and this the least accurate. Beyond what you have to do for the report, but this is just kind of a confirmation of the utility, we know that from that equation, we solve for milligram per milliliter. So it was stated that the stock solution that was given to you is 0.100 or so. And we created that by weighing out BSA, taking that weight, adding the appropriate amount of water. Sometimes the BSA could technically stick to the plastic in the tube. There might have been error in the weighing. There might have been error in the amount of water added to make up the stock solution. So you're supposed to read the absorbance of the stock solution, and then calculate what it should its actual concentration is. So for this lab, we just said use 1.00. It makes the calculations simpler. And also, though, if you were to do this yourself, then you would take that concentration, read it at least in triplicate, and then you would use that value. So how bad is it? How much off is the calculated our stock solution? I mean, I said it was 1.00. How accurate was that? We tried our best to make it 1.00. So what do we see in reality? Well, when we had made up the stock solutions saying it should be 0.5 milligrams per milliliter, we saw a certain absorbance. We can put that absorbance into the Y here, and we can calculate out a milligrams per milliliter. And now that was for 500 microliters. So if we multiply that by 2, that would tell us what the actual reading is. If we were very far off, these numbers should not be so consistent. And so what happens is for each of them, you can actually backtrack what it seems the stock solution was. And we see, and you do that, like say, so for 0.2, this reading then, if you multiply it by 5 and divide by 2 and multiply by 2, then actually that should give you a reading of 1.01 milligrams. So you see that in actuality, remember there's error involved in all these measurements. We see that for the most part, they are close to 1.00. If you had to do any adjustment, you might say maybe it was 1.01. The greater the amount should be the 0.5, which means you added 250 microliters of the BSA solution. There should be the least variation in the pipetting errors. There should be less pipetting errors. So this value is probably the most reliable. So to say that it was 1.00 milligrams isn't so far off, and it gives you, and considering the inaccuracies that you see just from pipetting error, that 2 decimal places out isn't so significant. So this is the data, and that's how you will complete your lab reports.